The dairy industry contributes approximately 2,000 million tons of carbon equivalent emissions annually, mainly in the form of methane, accounting for about 3.4% of global emissions. In the US, around 43% of methane emissions from dairy farms originate from manure storage. During storage, microbes digest organic matter, producing carbon dioxide, methane, and other greenhouse gases. Notably, liquid manure systems generate emissions that are 5.7 times greater per head than those from solid manure. Macdonald Campus Dairy Farm is home to around 80 dairy cows, producing around 1 million gallons of liquid manure per year. This manure is stored in a 560,000 gallon tank behind the farm and is emptied twice a year to fertilize the field. However, due to the high phosphorus content and the risk of nutrient runoff, not all of the manure can be applied to the fields, and instead excess manure is given away freely. This liquid manure is a very important resource for the farm due to the nutrients it contains. However, current manure management practices lead to the off-gassing of greenhouse gases that could instead be captured and used as a resource. Anaerobic digestion provides an effective solution to greenhouse gas emissions. By ensuring anaerobic conditions, it facilitates methanogenic bacteria activity. These bacteria break down the organic matter in manure, producing biogas. The released biogas is composed of 50 to 75% methane, which can be captured and used for energy. In addition, this process creates a nutrient-rich byproduct known as digestate, which can be applied to the field as fertilizer.
Considering all these benefits that come from incorporating an anaerobic digestion system to dairy operations, we propose the implementation of such a system for the Macdonald Dairy Barn. More specifically, we are proposing a single-cell covered anaerobic lagoon. This design consists of installing an impermeable plastic cover over the pre-existing manure pit. This will trap volatile substances from manure and create an environment that promotes biogas production. However, this system requires temperature above 15 degrees Celsius to be effective, since microbial activity in manure is inhibited at lower temperatures. In Quebec, we have cold temperatures during winter, so we have chosen to use a cover material that transmits a large amount of sunlight while also being resistant to heat losses. This material is bubble-structured PET. According to our heat transfer modeling, this material will allow us to have an average temperature ranging from 10 to 18 degrees Celsius during colder seasons and from 24 to 30 degrees Celsius during warmer seasons. These temperatures are crucial for biogas production. Similarly, keeping the manure in the anaerobic digester for longer periods of time, meaning over 2 months, also increases our biogas yield. For our proposed system, manure will be kept in intervals of 6 months in the digester before being emptied to be used as fertilizers on the fields. These two factors then make it possible for our system to produce around 27,000 meters cubed of raw biogas per year, or 76 meters cubed of biogas per day. This biogas can then be used in a biogas-specific furnace for heating, converted into electricity, or refined into a methane-rich composition called RNG. Since cost is a limiting factor, we have opted for a biogas furnace. This furnace should be able to provide the dairy barn with around 90,000 kilowatt hours of energy for a whole year.
Our design will reduce the Macdonald Campus Dairy Farm methane emissions by around 30%, producing energy that can be used in place of traditional natural gas. This will reduce the overall carbon footprint of the farm, helping reinstate the Macdonald Campus Farm as a hub for agricultural innovation and sustainability.